Having talked about integers, it's now time to turn to fractions. In order to discuss fractions, why don't we order a pizza? Here it is. We want to share this pizza with another person. How to do this? One way would be to cut the pizza across at its widest point, thereby creating two equal pieces, give one to the other person, and keep that one for ourselves. This illustrates very clearly the concept 1 piece out of 2, the fraction 1/2. However, a pizza can also be cut into 4 equal pieces by 2 cuts, as I've shown. In that case, you would want 2 of these pieces. If you took 2 of them and kept them for yourself, you would have 2 pieces out of 4. Now, 2 out of 4, if you do the prime factorizations, of the number 2 and the number 4, you see the 2 cancels out and you get back to the fraction 1/2. In other words, 2/4 is the same as 1/2, except that 2/4 is a reducible form of the fraction, whereas 1/2 is an irreducible form. To see how to reduce more complicated fractions, consider this one. What we do is the following. We write both the numerator, that's 30, the top part of the fraction, and the denominator, 132, the bottom part, in their prime factorizations, and then we cancel out top and bottom whatever we can. In this case, the 3's cancel out and one of the 2's, and you're left with 5/22. That's an irreducible fraction because 5 is a prime number. Another type of number we need is the negative integers. In our modern era, it's probably easier to imagine negative numbers than it was in the distant past. Anyone who has a credit card or a bank balance knows all too well that numbers can be negative. Another type of number we wish to introduce then, a class of numbers, is the integers, z. You put all the integers together, the natural numbers and the negative integers, and you have the set of all integers called z. The set of rational numbers, denoted q, is the set of all fractions a over b, where a and b are chosen among any integers. The only problem is you have to avoid 0 for b because division by 0 is not defined. Notice that in reading the name of the set Q, the description rather of the set Q, you say a over b such that, and so forth. The colon is the 2 dots there, is a way of describing a set, and it stands for where or such that. Now, do the rational numbers suffice? That's a question that worried the ancient Greek mathematicians for a long time. I mean by that, are the rational numbers enough to describe all kinds of reality? In order to answer that question, let's again order a pizza, but this time a square one. As you can see, the side of the square is 1 unit. It could be 1 foot, it could be 30.54 centimeters. It's just 1 unit of length. And again, we wish to divide it between 2 people. How do we do so? Well, we could just cut along the diagonal of the square. That would clearly be fair. And then we'd be left with a 1 triangular piece. What about the length of the cut in this case? The number I'm calling here h. What can we say about h? Well, a lot of light is thrown on this question by recalling the classical theorem of Pythagoras, which says that in a right-angled triangle, such as I've drawn here, the sum of the squares of the 2 shorter sides is equal to the square of the longer side, called a hypotenuse. In other words, this formula holds. If we apply this fact to our piece of pizza, you see that h squared is equal to. That is, h is a number which, when multiplied by itself, gives you 2. We usually summarize that by saying that h is equal to root 2. That's the radical sign that I've put around the 2. Now, h is a very real number. It's easy to see that it's bigger than 1 and it's less than 2. And the question is it a rational number? It turns out that the square root of 2 is not rational. And I'm going to prove it now. This is a challenge proof for you. You don't need to follow this proof to follow this course. Why am I doing it? For the fun of it, and because it's beautiful. Here's the proof. We're going to use a method of reasoning called reasoning by the absurd. We're going to suppose that root 2 is in fact a rational number of the form a over b, and we're going to derive from that a contradiction. The existence of the contradiction will prove that root 2 could not have been rational. Now, in writing root 2 in the form a over b, we can certainly assume that the fraction a over b is irreducible. So there it is, root 2 is given by that. If you square both sides, then you attain this equation. That certainly implies that a squared is an even number, because it's equal to 2 times an integer. Therefore, a squared is divisible by 2. That, in turn, implies that a must be divisible by 2. Because if a had no 2 in its prime factorization, then neither would a squared. If a is divisible by 2, then a squared is divisible by 4. That means 2b squared is divisible by 4, because 2b squared, we just saw above, is equal to a squared. It follows then that b squared is divisible by 2, and by the same reasoning as for a above, therefore b is divisible by 2. Now step back for a moment. We've proven here that a is divisible by 2 and b is divisible by 2. Well, there's our contradiction, because we said that a over b was an irreducible fraction. That contradiction ends the proof. That square box that has just appeared, by the way, is the way modern mathematicians mark the end of a proof. In the old days, you used to write QED for a certain Latin phrase. Now, we can locate numbers such as root 2 on the real line in a useful way. Here's how it works. We give ourselves an infinite horizontal axis. We're going to be calling it the real line. We choose a point on this line where 0 will be fixed. Now, once we have selected a unit distance, 1 unit distance, we can place all the integers subsequently. We put the positive ones to the right and the negative ones to the left. Once we have these numbers placed, we find it fairly easy to place any number on the axis in the following sense. If I want to know where root 2 should be, well, I know it lies between 1 and 2. I've already made that observation. And it should be right around there. And I can place it by simply taking my piece of pizza and having one end at 0 and the other end will fall at root 2. Of course, that could be a little messy. I don't suggest you do that at home. Now, the set of all numbers on this real line is denoted R. It's the set of real numbers. It is the end of our quest for numbers. As you see, it's the biggest class of numbers. It is a beautiful class of numbers in which to do much mathematics, for instance, calculus, and we'll be talking about it in the next segments.